Okay, maybe you all can take a look quickly the sample paper. Okay, we take a look at this part first. Okay, then later, okay, don't worry first. Later I'll give you time to work on the remaining lab 5. Correct? So in the meantime, if you look at if you go to learning material under week 6, under the practice test review. So this week is kind of like a breather for you to breathe. Okay, where you can look at this sample paper. This one, are you able to see this paper? This one, yeah. Can you look at it? The sample paper. Okay, so there's a question here under the sample paper, right? Are you able to see the sample paper? There's a question which I want to just briefly touch on. Okay, so for example, a question like this may appear. Okay, question like this may appear. Let's take a look, shall we? Now, those of you, just a friendly reminder again, the lab 4 exercise 8, I must see it. I must see your video inside the, bright space. Because you don't submit the video, you submit just paper, to me, no use. You know what I mean? I need to see your video. The way you do the thing. Okay, shall we take a look at this question first? This one, sample paper. You know where to find this? Under week 6, everybody. Nok can find this paper. Then week 6, you all know where to find. Yeah. Xavier, you know where to find the paper? This one can, okay, under week 6, okay? Week 6, this week one. This week is week 6. Sample paper, put there. Okay, so allow me to just quickly touch on this one first. Then after that, we move on to cover the other side of the things called the code weave. This one. Okay, so if you got a structure like this, okay, where you have a for loop. Okay, this is a for loop, I hope you know. Okay, I have a for loop. I have a for loop as a count, right? Maybe you want to take note, very important. Take note. Okay, for loop here. Okay, a for loop, then we can set a number to it, right? This n. What is n? What's the purpose of setting an n here? Means what? Anybody know? What is n for? What does this mean? Number of iteration, correct. Okay, so that means that what we say is the number of time you will execute this for loop, right? It's a bit different from while loop, right? While loop means you got to run and then you must press a stop condition and you will terminate. Otherwise, this program will just keep looping. This one will loop 3 times. Okay, maybe you want to make some notes. This one was covered in your lab 2. If you recall, if you got your lab sheet with you, right, written you in lab 2, one of the exercise. I can't remember which exercise, but it's definitely in my lab 2 lab sheet. You can take reference. You take a look. I've given you the mark paper so that you can revise. Okay. Now today don't rush. Don't need to submit lab 5. Okay. Today don't rush to submit. But if you got lab 4, it's good. You got your lab 4. Okay, you can. Some got no grades. Those who get A and above one, you have a grade there. Then the rest will be the other grades. Okay, other grades. Will be other grades. Okay, there's an extreme. So you are the in between. C1 because they never submit the video. I cannot access. Okay, as I told you already, unless you say, oh, sir, I want to go and do the video, can you help me remark? Possible. I will consider. Okay, if you don't do, then no mark. Okay, okay, let's talk about this one first, shall we? Yeah. Okay, so it's I try to reinforce positive behavior. Positive behavior means that you do good. I will encourage you. If you don't get anything here from me, that means I better do something. So that I want to receive the praise or good remarks. Understand? So this is how I try to do it. I won't scold or anything. That's not my style. I won't scold you. Just that you don't get the so-called acknowledgement. Then you know it's something I must do something. Those who do well, I will praise you. I'll say good. Put you on good list. Okay, so you try to keep yourself motivated, then I want to be on this good praise group. Okay. Now let's take a look at this, okay, shall we? If we have a for loop, okay, like this, okay, a typical sample paper question like this. Okay, now I have she registers here, right? Look at your lab 2 also, if you want to recap. Okay, I got the question may ask you, okay, couple of things can possibly come out lah. Ask what is the value for the output? Okay, you need to show that you understand how this thing works. Okay, so please focus on this for loop, this diagram here, this block diagram here. Ignore this part first. Okay, so what I may recommend you, okay, if I got something like a wait timer, okay, if you recall, if I set it to a number, okay, let's say if I ask you, right, if I set this one to 200, let's say, if I put to 200 here, what is happening? Do you all know? What is the implication? Xavier cannot see, Xavier. The pillar block you. Later can come forward, later or take picture. Cannot see, then come forward. There's some seat here. Yeah, those who cannot see one, come forward. Come nearer. Cannot see, sorry. Cannot see, come nearer, okay? Okay, so what do you think? If I set to 200 onto this wait milli, right, how many times will it run this loop? I mean, in terms of the how many times per second? That means the loop rate. I'm asking you, what is the how many times per second? Per second. How many times you will run? If I set to 200 here. How? How many? 5 times. Good. 5 times. Okay, how I get 5? How you get 5? 200 millisecond is what? This is 200 means 0.2 second, right? 200 millisecond to convert into second is 0.2. So it's actually running at 0.2 second one time, right? So in 1 second, it will be 1 second divided by 0.2, right? So it's 5 times. Do you understand? So in 1 second, it will execute 5 times. Oh, okay. So you see this, don't get alarmed. So this number can change, right? Can ask you anything. I can put to 50, put 100 or whatever. You be able to tell me how many times per second. Okay, and please write down. If you need to make notes, please write your own notes. Okay. Okay, now next question. Okay, in this for loop here, okay, I got she register. I hope you know. There's a she register here. What's the purpose of the she register? Is to store the number, right? It's like a memory, right? So that you will store the calculated value inside here. So on the next iteration, right, this value can be bring forward here, and then you pass on to continue the calculation, right? Remember this? Okay. So typically they may ask you, okay, they put some label, let's say maybe A here, B. Okay, why don't you explain how this thing works and tell us what is the final output result? Okay, so you need to work out. Remember, you don't have a computer. This one is theory test. Only give you a block diagram like that. You have to analyze it. Okay, and then work out. So maybe what I suggest to do. Okay, if I were you, you will ask to put a table. So put a table. They're specific. They will be specific. They will tell you to put a table. If you don't see the table, 0 marks straight away. Okay, don't just put the final answer. Don't just say output is this. Then you get 0. Okay, if you put output value equals to 21, let's say, you just put like that, this one will be straight away 0 because I need to see your working. Okay, so what you suggest to do, you must put a table. Okay, put a table like this. Let me put this camera a bit this side so you can see the whiteboard. Okay, the camera is watching it, it's recording. Okay, table like this is good. Scroll down a bit. Hopefully, this webcam can capture the table. Okay, so let's start. Very easy. Okay, so you got the stack sheet register here. This thing is a stack one. So A and B, put a table like this. Very easy, right? So you can put the n has an iteration. I put an n here. So you get 1, 2, 3. Right? How I get 1, 2, 3? Well, you should know that this is a for. Hey, you guys cannot see. Very scared. Why you all see that, Atish? Praveen, see here. Praveen, see here. See in front. You all cannot see. You all pillar blocking. I cannot move the pillar. Can ah? You see, don't shy, don't be shy. No solution. You work out first. You must work out. You see me? Okay don't know You see Cannot see y'all. I don't know how you can see. Y'all got bionic eyes Bionic eyes can see through the pillar. Okay, never mind. So n equals to 1, 2, 3, right? How I get 1, 2, 3? Because I know here got 3 count. Okay, so that means that you will execute 3 iterations, right? 3 iteration or 3 counts. Look at your lab 2. Lab 2. This one nothing new. This one, what is tested is what you have learned. Nothing that come out from the blue sky. Okay, you have learned before. Right, so I put 1, 2, 3. Alright, so what's your A value? Can I ask very quickly? So I can see. Good. What is your A value? When the program run, what's the A? 4. Okay, you help me. You can participate. 4. Okay, so of course B will be the summation of these two, right? Because this is sum. Okay, you cannot see the. Why A is 4? Atish, why A is 4? Alright, throw at him. Why A 4? Huh? Why A 4? Huh? Next week. Yes. Okay. Only 20 and 35 minutes. So it's about 55 minutes. Okay. Why 4? Very good. Then the initial value is 4. Initial value is 4. Okay, it's 4. Okay. So 4 and 7 is 11. Thank you. 7, 4 and 11. So B is 11, right? And okay, so 11 is here already. So on the next cycle, what happened to this 11? It's here, right? Just now it's here, right? I mean the last, this is the shift register. So the value here. Then what happens? The next cycle, this value will be come up to here, right? So here the 11 come to here. Am I right? So I cross out it first. Okay, so what happened? But these two, these two come down to here. Thank you. From here come down to here. A bit messy. Never mind. It's okay. So what is the next value? That's A. 2, yes, very good. 2 is here. And because 2 plus 7, right? So your B is 9. Okay, very simple. So then what happened next? Your result here is 9 now, right? So the next iteration, what happened? This one will go here, right? Then what happened to your 11? 11 will drop down to here. Alright, now your just now 11 drop to here. Then the 9 go there. Alright. Okay, so your third iteration, what happened to your A? What is A? Yes, thank you. That should be easy. So 11 plus 7. Okay, I know you can calculate. Okay, so, and when this cycle stop already not? Has it finished? After n is 3, will the while loop stop? Yes, so what is the output value? 18. Thank you very much. 18. Okay. Okay, good. So you all go and write your own notes. Something like that come out. Maybe. Maybe. Huh? Of course won't. No logic, right? I give you 99. Right. Not be right. Won't 99 jalan lah. Okay. Then think about it. Think about it, right? If you still have your lab 2, I don't know, exercise 3 or something. Is it exercise 3? 3A, right? Exercise 3A. You still have your VI, right? You can go back and revise the VI. Maybe turn on the highlight execution and then you can see the value run. Yes, question. Not the 0 one is for this one. The for loop also got this I. The I start from 0. Okay? The I value, remember the iteration count. You will start from I0, I1, I2, then you stop there. Yes. And 1, 2, 3. 3 count only. Obviously, we don't put something like 99 lah, stupid right? So 99 how to do? I also cannot do it. You ask me 99 how to do? Okay? Can do lah. I mean, you got software, put inside let you run and then see only mah, right? But you are not going to do that. This is just a simple, just test your concept. See whether you understand what is Shift register. Okay, so please make some notes. Okay, so I think sample exercise quite important if you ask me. The sample paper so good your sample paper. Oh, okay. Okay, no question I go on now. Okay, the next one I want to talk about. You notice that from the sample paper got question 3, 4, 4 got 2 parts, right? 4A, 4B. Okay, this one I haven't really talked about because I want to leave the theory as like today, so that the thing is still fresh in your mind. Right, so let me explain. Okay, let me just pull out the slides. Are you able to find the slides? I think it's week 4. The deck of slides. I downloaded already. I got one copy here, but I believe if you navigate to week 4 in your Brightspace under week 4 learning material, right? There's this thing called Introduction to Data Acquisition. So for me, I already got the slides ready, but if you can find it, please follow along. This deck of slides, I'm sure you have seen before. This should not be new or alien to you. This one I've shown you before. This one is under week 4 if you want to follow, go to week 4, the folder there. Then you can see the PowerPoint slides. Can I just quickly recap this one with you? Okay, so what is resolution? Resolution means how many bits you use in the DAQ. Okay, now can I ask you, okay, you all have the DAQ hardware in front of you or not? On your table? Do you have one box? If you don't have one box, go and grab one behind. Okay, if you don't have the box, right, the demo box. Go and grab one. Grab your table number one. Go look at your table number, then go and grab one. Okay, can I ask you how many bits that one does it contain? The DAQ. This one, how many bits? How do you see? How do you know got how many bits? Look at the box. Look at this one there. Look at this one. You all don't have the box. Go and grab one. There the box here got put you. The NI USB 6009. Yeah, the National Instruments, right? How many bits? That one is how many? 14, is it? 14 bits. That one is 14 bits. Okay, 14 bits. How you know? You can take a look at the box. Then the one they will tell you. Specify to you. National Instruments, how many USB, the model 6009, how many bits? 14 bits, right? So 14 bits means that one is the resolution. Okay, so the one is 14 bits. So the number of bits refers to the resolution. Can number of bits. Okay. Okay, then what is code width? What is code width? Can I ask you? What do you mean by code width? Okay, so let's take a look. Code width. Okay, so you see there's this thing. Okay, range, maybe you know. I start with range first. Range is easy. What is range? So code width refers to this formula here, right? Code width. This one is the range, right? Then this one is 2 to the power n. Okay, what do you mean by range? What do we mean by range? The range means is what? Is the maximum minus the minimum, right? So obviously if you remember your lab 4, lab 4 exercises, if you recall, if you have your lab sheet, some of you haven't submitted. The lab 4, correct. I asked you all to draw something, remember? The ADC one. Okay, so I will explain. Okay, so if you recall, I show you this. Okay, code width, this is not something that you must memorize or know. It's basically the voltage range divided by 2 to the power n. N refers to the number of bits. Okay, so I believe we have seen this before. This one should not be new to you. You also have sketched this inside your lab 4. Okay, where you can see on the slide here. Okay, for a case like this, the range is given, as you can see. Minimum is 0 volt, maximum 5 volts, right? So the range means 5 volt minus 0, so it's 5 volts. Okay, so if I ask you, if I tell you that I have a setting minimum -5, maximum +5, what is the range? 10, very good. I say -5, minimum is -5, maximum Vmax is +5. So from -5 to +5, the range is 10 volts, correct? Okay, you understand? So that it means by the range. Okay, now the number of bits, that one usually is specified on. Okay, so take a look at this example that was given to you. This is a 3-bit system. We know that 2 to the power of 3 is 8. Right, 8 means like something like 8 steps, if you like. You see this diagram, right? Obviously, if you bring back your knowledge of power electronics, I'm sure you all learn power electronics, right? Okay, what does this waveform look like to you? Any thoughts? Anybody? This waveform look like what? It's what is it called? There's a name for it. It looks like, but not really, right? Sine wave means got negative swing, right? So this one is what? Start with the letter R. Right? What kind of waveform? What kind of waveform? Yeah, sine wave is partially correct, partially, because it's not exactly sine, because sine wave means got positive swing, negative swing, positive swing, negative swing, right? Yeah, rectified, correct. This is a half rectified waveform. Okay, if you like, almost or rectified waveform, right? Rectified means only the positive cycle. Okay, almost like as you can imagine. Okay, but this particular 3-bit system has very poor code width. Why I say that? Because code width means the range, voltage range divided by 2 to the power of n. In this case, I put it here. The range is 10 volts, right? Is it 10? No, 5, 5 volts, sorry. In that case, I put 5. That one is 5, right? Based on this example, it's 5, but on my board, I wrote 10, but it doesn't matter. Okay, but you look at the whiteboard one first. No, sorry, you look at the projector one first. Okay, so that one, the range is or sometimes they call it the span, V span, voltage span. Actually, it's the same meaning. Right, it's 5 volts. But 5 volts divided by 2 to the power of 3, which is 8, right? Okay, if you use your calculator, you key in 5 volts divided by 8 so-called levels, you get that the code width is 0.625, but which is very poor, if you ask me. Okay, it's very poor because why? The waveform is almost like got staggered, like a staircase type of pattern. You see, but obviously, in the back of your mind, you know that this one is a half wave rectified sine wave. But this waveform is not represented properly. Why? Because the code width is very poor. Because every step is 0.625. How I get 0.625? I take 5 volts divided by 2 to the power of n, or 8. 5 divided by 8. I get 0.625. Right, this one is done in lab 4 before. Now, if you progress one level better, one level ahead, okay, this one better waveform. Why? Why better? Because actually at the end of the day, right, you want to make this thing small. This code width, the smaller the better. Okay, this code width, right, the smaller the better. Now, this is the result we show you. This is a 4-bit. Just now was 3-bit, right? Now it's 4-bit. How to make this code width small? Very simple. Increase the n. This one, right, you increase. 3-bit become 4-bit. Then this is the resultant. It's better because the number of levels is increased. So if 2 to the power of 4, right, is 16 steps. 16, right? You agree, right? 2 to the power of 4 is 16. Okay? Assuming that the voltage range remain the same, unchanged, 5 volts. So now you're getting 5 volts divided by 16. You see? 5 divided by 16. For those of you on this side, same thing. 5 volts divided by 16. You see? 5 volts. How I get 16? Because 2 to the power of 4. Right? 2 to the power of 4, I get 16. So 5 volts divided by 16. You notice that the code width even smaller, half of just now, that one, 0.625. This one is only 0.3125. Much better, and you can see that obviously the waveform is getting better. Right? Agree? Better. Now let's make it even better. How about here? Wow, this one better, right? This one is 8 bits. Okay, 8 bits is quite a good representation. You can see it. 8 bit because 2 to the power of 8 is 256 steps. Okay, 256 steps. Now, assuming that, again, we keep the voltage range constant or the same. So you take 5 volts divided by 256, you get a very beautiful half rectified waveform. As you can see, very good representative of the sine wave, or at least a rectified waveform. Okay, positive side only is called rectified signal, right? Your power electronics, right? If you all remember what you all learned. I used to teach power electronics, yeah, but I think it's quite fun. Power electronics, quite good. Okay, so you can see that the whole idea is to tell you that, hey, the code width, I want it to be as small as possible. Okay, and then I can, but of course at the expense, there's a cost involved, right? If you use something ADC, of course I can just without limit just increase the number of ADC bits, but it's more expensive, just to let you know. The number of bits increase, your ADC, the chip, is more expensive. Okay, got those very high end one, 32 bit, 64 bit ADC, all those kind of things are very expensive. The more bits, more expensive. Just like your phone, right? Your phone, your smartphone, more memory, 128 gig. No, I think 128 is normal, right? Cannot be, now cannot be, not enough, right? Now like things like people go for 256 minimum, right? Or 512. Got anything bigger than 512 or not so far? The handphone got 1 tera, man. Have have I didn't know that. So time to check out. I didn't know that. Okay. All right. Okay. So summary is that you must memorize this. Please remember this. The code width. This one. You will be tested on. Okay. Code width. You must know this. All right. Then range. I don't need to explain. This one. Okay. I'm going to bring you to two scenarios. Very important. This one very important. Okay. Very, very important. You must know this. Let me explain. Okay. Let me explain these two cases. You must know. All right. That is your sample question 3 and 4. Okay, let's take a look. Now, consider this. Now, if you have, say, a sensor, okay, maybe I just draw here, maybe any temperature sensor. Okay, temperature sensor. Okay, so maybe this temperature sensor output, remember, your sensor, right? This temperature, thermometer, this temperature sensor output is in what? What is it? Output, voltage, right? Remember we are electrical engineer. Remember, we are electrical engineer, right? So we talk about electrical signal, right? So the sensor output is electrical signal, remember. The output from the sensor is some form of electrical signal. It can be voltage, can be current, can be resistance, or any other thing. Okay, but generally, if the output is voltage, it's very normal. Okay, so let me give you an example. I got a temperature sensor. Then I skip. You notice I gray out this yellow box. You see my diagram there, right? Okay, but I think you can read, right? What's the word there? It says what? What do you see there? The one, the gray out one, the little box, the yellow box. It says signal conditioning, and then it says amplifier, right? Okay, I'm going to explain later on. What is the consequence with and without it? Okay, I'm going to explain without first. Without. Okay, there are only two cases only. So it's now without. Then later on, I'm going to explain to you what happens if you have it. Okay, there's one with, and this one is the with. This one is the without first. Okay. Now, so what is the thing that we are trying to do? Okay, I'm trying to explain here. Okay, now a typical question like this is that they will tell you the ADC, analog to digital converter, as you know. Okay, now every electronic, right? There's always specification, right? They'll tell you what is the voltage input, what is the range, then what is the output range. They will tell you one. Okay, you read the data sheet, they will tell you, this one the input is between 0 to 5 volt or 0 to 1 volt or whatever. All right, then the output is also something output. Okay, they will specify. So you must read the data sheet carefully. Then it also will tell you what sort of voltage. Now, if you put in something 20 volts, you think can or not? To the ADC. Cannot. Usually you think cannot. It's outside the range. What will happen if you put in 20 volt? You may fry the chip. Okay, you know what I mean? Fry. Then smoke come out. Okay, so don't do that. So we follow. Okay, now what happens is this. First step. Case number 1. Now what happens if, okay, I draw this one first. I draw on the board here. So I got my ADC, I draw here. Sorry, if you all cannot see, please highly recommend you all just wander up here and then you can see in front for a while, no problem. Okay, you can come forward here and see. Okay, so don't worry. Now this ADC, it has been specified is 8 bits, right? So I'm going to just quickly just sketch something like that. So I'm going to tell you the range. Now, based on what I drew here, right, as you can see, now your sensor output, okay, maybe I start off with looking at the sensor first. Okay, so if I may ask you, quickly erase this. Okay, so if I ask anyone here, okay, let's say if I see that this one is, okay, now what I just show you here, okay, for this particular sensor, you can see, it says that the sensor output is between 0 to 1 volt, right? 0 to 1 volt, and it corresponds to a temperature of between 0 degree to 100 degrees Celsius. Okay, so which means that this one is your temperature is actually is what you want right now. It's the output, right? So then actually both are output but what I mean is that I shouldn't like that put. I just don't say input output. Don't. I just put as if I tell you, okay, if I plot, imagine I got y-axis, got x-axis. So if I put temperature here and then I put from 0 to 100, then on my horizontal axis, the x-axis, I put here 0 to 1 volt. Okay, you know that this is a linear function. Straight away you should come to your mind. Hey, this thing is linear. So if I may ask, what happens if I tell you, I take a multimeter, I measure output here, right? Imagine, I put a DMM here. Okay, I measure this output, these 2 points, one with respect to the other. And I tell you, hey, I measure 0.6 volt. Okay, can you tell me what is the temperature? If I measure here, right, if I got multimeter, I measure, I tell you the characteristic already, between 0 to 1 volt, it will give me from 0 degree to 100 degrees Celsius. Now I say, hey, I measure here 0.6, 0.6. What is the temperature? Can you tell me? 60 degrees. How do you know? Because it's linear, right? Obviously, very good. Thank you. 60 degrees is correct. Because every 0.1 volt is 10 degrees, correct? Correct. 0.6 is 60 degrees. Agree? Do you agree? Linear function, very easy to work. Always very easy. Linear. Nice straight line, right? So you can tell me straight, okay, easy one, linear. But now, okay, having understand this, very simple concept. Okay, I hope you all know. You all know what I'm saying? I hope you understand. Okay, then now come to here. Okay, now this thing, right, is connected directly. I say directly. In this case, I connect direct. Okay, direct connection to the ADC. Okay, but you obviously spotted something already. When you look at it, the voltage like a bit not the same. Okay, no? The output of the sensor maximum is 1 volt, right? But your ADC is between 0 to 10. Okay, 0 to 10. Alright, so you register this in your mind first, okay, before I tell you other things. So don't worry about this one first, the computer, never mind. Focus on the ADC first. Okay, although it's good that it is well within the 10 volt, right now, 1 volt is less than 10 watt, so should be okay, right? But what is the problem? Okay, let me explain it. Now consider looking at this. So this is still the same case, direct connection. Okay, I draw a scale here, a ruler scale, as you can see over here. So the ADC is the scale there, is from 0 all the way to 10 volts, as you can see there. The green color, that one is the sensor. Okay, the sensor is only 0 to 1. Do you see that? So what is the problem? Is there an issue here? Yes, there is something. Okay, let me explain. So if you can see, if I draw the so-called ruler scale and I say this one is the ADC, right? Your sensor is only your sensor only occupy 1 volt, right? 0 to 1 volt, correct? This part. Okay. So can I ask you also now, what is the discrete value? The digital value. I call it the discrete. This one, how many bits? Can I ask you? How many bits is on this ADC? How many? How many bits? 8 bits, right? So 8 bits means we know that 8 bits means 2 to the power of 8, right? So it's 256, am I right? Agree? But of course, your discrete value will be from 0, 1, 2, 3, 4, all the way until 255. Do you agree? Why 255? Because you minus 1, right? Right, 2n minus 1. Because 0 included. So total there are 256 steps, so to speak. Agree? Yes? Okay, very good. So then what is the problem? Okay, because you only occupy up to 1 volt, so that means you only use up to here only. So up to the discrete level. So how do I work out what is this thing? So what does it mean? So can I say that we only use 1 volt out of 10 volts? Can you agree there? I'm using 110 only. 1 volt, right? The whole thing is 10, right? But I'm using 1 out of 10, right? 1 out of the whole thing 10 times 256. So I get approximately about 25 steps. Do you agree? This one is a just linear relationship. Do you understand? Everyone don't agree? Do you understand? Do you understand why I get about 25? Because I take 1 volt, out of the whole thing is 10, right? So it's a ratio thing, right? 1 over 10 times total number of digital steps, 256. So I get about 25 steps. Okay, now you will observe further that the question may ask you what is the temperature per degree step. So you can see from the solution at the bottom, what is being explained there, you will notice that it's actually, you take 100 degree because the temperature sensor output 100 degree. So 100 degree divided by 25 steps, you get 4 degrees per step. Okay, which is awful, if you ask me. Super awful. I will throw this out of the window. Because 4 degree per step is very poor. Agree or not? Because every time you measure is 4 degree. Anything in between I cannot capture. Understand? That means if I got something I want to measure like 2.8 degree, I cannot see it because my resolution is 4 degree. The next one is 4, 8, 12, 16, and so on. Do you understand? So it's very, very poor. It's just like the same example like what we did just now about the rectified sine wave. Same thing. You get this jagged thing, right? Okay, so how to solve this problem? Do you understand so far up to here? Any question? Livia, any question? Slowly try to understand. Any question? How I get 25? I still don't ask. How I get 4 degree? I still don't get it. I can explain again in case. Do you understand? Question? So what is the code width for this guy? Later you ask me. What is the code width? Yeah, okay, wait. Okay, this is the first case, first scenario. Because this case got amplifier or don't have amplifier? This one. Can I ask this one, is it with or without amplifier? Recap lah. No lah, of course, right? No amplifier. Okay, so you notice that no amplifier. The whole idea is this, okay? Listen, the whole idea is this. Your sensor output must match the ADC fully. Okay, you must match. How to match? Very simple. Amplify the signal. Okay, you see what I mean? Later I show you what the next example. Case 2. Only 2 cases only you need to know. This one no amplifier. You see the green color one? It's just the 1 volt only. No amplifier. Not match. Does not match. The whole objective is that you must match. Why when you match, what is the benefit? Okay, let's watch next. Yes, the code width are smaller. Okay, this is the condition now. I'm going to tell you. Okay, I'm going to introduce an amplifier. Slot in between this guy. Before the sensor connect to the ADC, I use the amplifier, amplify the signal first. Okay, but how I know how much to amplify? That's the question, right? I believe you may ask me, hey sir, how I amplifier, but how much? How many times? Okay, so how do you know? Very simple. Okay, the sensor output 1 volt, your ADC 10 volt, you take this, divide by this. This max value divided by this value. Correct or not? The ADC, the V max of the ADC, This one, this is the ADC, right? Divide by this one. What's the sound? Some computer, the temperature max. You take this one, divide by this one. Okay? So it's what? 10 volt divided by 1 volt. So amplifier gain got any units or not? Can I ask you? You all got study op amp or not? Can I ask you? You all never study analog electronics. Got study or not? Electronics? Huh?
Yes.
Huh? Got You see? Jack say got.
Correct.
You all got study op amp or not? Operational amplifier. Never. Oh my god. How can you all don't study? You all never hear before. You all never hear what is op amp? 741. Got hear before?
No.
Never? Oh no. Serious? Never study this operational amplifier. Okay, never mind. Okay, so the gain in this case is 10. Okay, in case you wonder how I get the 10, very simple. I take the maximum ADC voltage 10 here, divide by the sensor voltage 1 volt. So it's like here, this one 10 volt, divide by this fellow here 1 volt. Okay, 10 divided by 1, so it's 10. Okay, it means that I'm going to amplify this signal 10 times. Okay, let's take a look. So 1 volt amplified by 10 means 10 volts. Okay, this is the condition. Just now was 1, now I fully utilize. 1 volt, I extend it 10 times because I multiply. Gain, amplifier gain. Yes, now you fully use the whole ADC. Correct? You use everything. So it's the full range. So now if I ask you what is the code width or the degree per, what's the so-called the change in temperature per step? I'm going to take 100 degree this time, divide not by 25, divide by the whole thing, which is 256. Okay, I divide by the whole range. So I get 0.39 degree per step. You can use calculator and check. You key in. Okay, do you think this one is better? Smaller than just now? Just now the one was what? 4 degree per step. This one is 0.39. Much better. Much better, you understand? So your code width is smaller this time. Okay? Because you improve the performance okay, by fully utilizing the ADC. So there's a penalty. If you don't use the ADC to its fullest, you're going to suffer. Your signal will suffer. Understand? So in this case, it's pretty good now. I'm happy because I amplify 10 times. You cannot do anything more than that because your ADC is 10 volt means is the max. You really try your best. Amplify 10 times, this is the outcome. Okay, so I hope you get some idea. This one was actually inside your lab 4. I think inside your question. If you all still have your lab 4, if you want to still come back and take a look at your lab 4, you can have a look first. Then your lab 4, you still have your lab 4. Those of you submitted lab 4 one, you want to take a look first. Since I haven't marked yet. Xavier, give you back first. Don't hurry to submit. This one I give you first. This one is yours, is it? The green one I think is here. Give them back first. You all have lab 4. Some of you return you already. You all take back first. You all take a look first. And Xavier one. Xavier. Take a look first. This one is one of your questions. Sorry, yours left here. Lab 4 you never submit. Take a look. Then any question about this one is very important. That's why I recorded. And I think they recorded the screen also. I don't know whether the people there on the screen can see. But this picture here. So basically the same. This is the temperature sensor. Okay, the ADC here. Nothing is basically following the notes. Okay, any question for me? This one. The sample paper you all need to try first. We won't give you the working solution. You all must try first. Can Any question? I know some of you still stretching your head or thinking first. Think. Okay, maybe later on can ask me. Okay, you write notes first. Okay, later you can ask me question again. Can so I will hold on first. I will probably stop this sharing first and upload. This one I think can share with the other class also. So let's stop